Thank you. Welcome everyone for the DeCenter seminar series. This is our second in a row. We're privileged to have Professor Maurice Herlihy, who is a very distinguished researcher, distinguished scientist, and for decades now, working on a variety of topics, but primarily distributed systems, distributed algorithms, and now very much at the intersection of blockchains. This is a professor at Brown University, formerly been at Carnegie Mellon for quite some time, and his research is very influential, and awards have followed them. Good work followed by awards. And he's a member of the National Academy of Engineering. We're very happy to have such a distinguished researcher and very close blockchain influencer, follower, and talking about cross-chain deals. Thank you, Maurice.
Thank you very much. Well, it's a great pleasure to be here. I just realized that I've now visited all of the Ivy League schools. So I'm pleased about that. So what I'm going to talk about, there are a couple of papers that have the technical details. Joint work with Barbara Liskov, Liuba Shrira, and Inge Shui. So if you believe, as I do, that something called blockchains will take over the world, the one thing we know for sure is there will be far too many of them. That everybody was going to want their own blockchain. Bank of America is not going to share a blockchain with Barclays. The Federal Reserve is not going to share with the Europeans. So the world will be fragmented across lots and lots of blockchains. The same way the data in the world is fragmented across lots and lots of databases. And the question of how to make these compatible with each other is something that's going to be a problem, for a long time. It's going to be a challenge. And in particular, some kind of cross-chain commerce, where we're transferring assets of value from one blockchain to another. Being able to do that kind of reliably and safely is one of the big issues. Now, I'm going to put this in kind of context. The problem that we're looking at is we have people who want to trade things with each other. They want to, if the exchange goes well, then both parties benefit. But in the blockchain world, nobody trusts anybody else because you don't know who anyone is. You have no recourse to civil law. So, it's exactly like, doing things like drug deals. That, the reason that drug dealers use violence is because they can't sue you in court. Now, in blockchain world, we hopefully don't have either violence or courts. And so the question is, how can we cooperate with one another in a mutually advantageous way when we don't trust each other? And to me, this is one of the fundamental long-lived problems that we're addressing. And this is nothing really to do with blockchains. This is back in the Stone Age when tribes would meet and trade mastodon bone for flint. They would have the same kind of a problem. So I think this is something that's kind of fundamental, and maybe distributed computing is longest lived problem. So let me give you just a concrete example of what I'm thinking about, because I don't want to go through abstractions more than necessary. So here we have Bob. Bob is a theater owner, and he has a big pile of tickets that he wants to sell. And of course, he keeps his tickets on the ticket blockchain, or the ticket ledger, whatever you want to call it. Carol is a consumer. She wants to use her cryptocurrency to buy tickets to a show. Now, of course, if you want to see a Broadway show, you don't call up the actual physical theater and say, give me tickets. You go to a broker who is equipped to handle transactions at scale. So Alice, the ticket broker. Now, remember, the tickets and the coins are going to live on separate blockchains. So, this is what makes it kind of technically hard. And so they want to do a deal. And the deal is something like this. So Carol gives the money to the broker, Alice, doesn't communicate directly to the ticket seller. The broker takes a commission and then runs another transaction to actually buy the tickets from Bob, and then relays the tickets to Carol. So a couple of interesting things. This is not a direct swap. It's not like everybody is trading one thing directly for another. There's a level of indirection in here. This is, this idea of being a broker having levels of indirection is a very common property in this world. And in the end, presumably, everyone is happy. Alice got her commission, Bob got his cash, and Carol got her tickets. And the question is, that I want to ask is, what sorts of things are, what kinds of outcomes are acceptable here and which ones are not acceptable? So imagine that, again, this being the blockchain world where everyone can be secretly evil, Carol is just saying, all I want to do is I want to get those tickets for free. So I'm going to be as clever as I can and, hack this and that and the other thing. And what Bob is trying to do, Bob is trying to scam Carol. Maybe Alice works for a hostile foreign government that wants to create as much economic chaos as possible. And Alice doesn't care about making money. She's perfectly happy to spend lots of money as long as it does a maximum amount of damage. And all of these characters want to interact. So one thing that could go wrong, right, is that Bob could give away the tickets and end up not collecting his money. I think we would all agree that that is not a satisfactory outcome, even though a majority of the participants are perfectly happy with this. So that would be an incorrect answer, or an incorrect final state. Another possible outcome is Carol pays for the tickets but doesn't receive them, possibly because the others are conspiring against her. And that's also clearly incorrect. Alice could end up with extra tickets and coins, and Alice, cares about her reputation, but now she's got to go and do refunds and other kinds of, expensive and time-consuming things. So that's also not considered a correct outcome. Another possible outcome is nothing happens. The deal falls through. Everybody gets all excited about doing this transaction, and then in the end, you end up with what you started with. And that we'll probably agree is actually a correct outcome, even if it's not a desired outcome. And nobody ends up being really substantially worse off with this outcome. So we can take this outcome and this kind of structure and kind of generalize it and say, well, we can have kind of arbitrary, directed graphs of interactions. And typically what happens, each party wants to trade some assets, either directly or indirectly. Multi-step, brokerage is fine. Each asset lives on its own database or blockchain, ledger, whatever you want to call it. The parties are autonomous in the sense that we can't assume anything about their actual behavior. If you want to commit a distributed transaction with an Oracle database, well, all the software is written by Oracle. Pretty much you assume that the different branches of your company are not trying to cheat one another, and you can get a lot of mileage out of those kinds of assumptions, but we can't do this in this context. And nobody trusts anybody. So again, I want to emphasize that this is a fundamental problem. This isn't, a particular, this is independent of what the underlying blockchain technology is, at least to a first approximation. So this is certainly not about, Bitcoin or any specific blockchain. And I want to argue it's not even really about blockchains as such. The thing that I'm calling a blockchain, could just be a database. As long as it's, reliable, highly available, and tamper-proof, we don't really care whether we're using this year's technology or last year's technology. I'm really interested in what we build on top of these things. And it's sort of about how you can synchronize in a world where you don't trust anyone. Typically, there's, if you look at synchronization algorithms, you always assume that, maybe there can be failures, but you're typically not dealing with somebody who's actively trying to pick your pocket. So the papers that I flashed at the beginning of the talk, there's sort of two directions we can go in. One is I could talk about the actual mechanisms. We proposed a couple of different ways of doing these cross-chain deals. The mechanisms that we use is something called hash time lock contracts. There's an alternative approach where we use something we call the cross-chain proofs. So I'm not going to talk about that here because that would be a very fun talk for me, but I'm not sure it would be a fun talk for a general audience. This is something that is of intense interest to a small number of people who each think that they can do it better than the competition. So I'm going to focus on a different topic here, which is kind of a more general topic, which is the notion of correctness. What do we mean when we say that something is correct? So in the sort of traditional distributed computing world, which is my background, people often think about fault tolerance, they kind of anthropomorphize it. They say, imagine that you have an adversary who is trying to frustrate your purposes. The adversary could be trying to get you to get wrong answers. The adversary could be trying to make your computation as inefficient as possible. And so you put yourself in the position of the adversary, reason about your algorithm, try to find holes. This is a common practice. Now, in traditional distributed computing, adversaries have a kind of restricted set of tools. They can crash servers, they can delay messages, they can reorder messages. In the limit, you can do a kind of Byzantine failure under fairly limited circumstances. And the kinds of problems that we look at are very precisely defined mathematical problems. Consensus, state machine replication, things of that nature, where we can, they're kind of limited problems, they're very clearly defined, we can prove theorems about them, and so on. Now, in the modern world, this adversary now seems kind of almost laughably naive. So a modern adversary is far more powerful. In this case, we're not anthropomorphizing the adversary. The adversary really is a person, sitting in a cafe somewhere in Central Asia, reading your open source code, trying to figure out how to, drain your company's assets. And so this is a much more challenging environment than you would find anywhere else. The tools that they have are much more complicated, much more sophisticated than the simple failure models, much harder to pin down, much harder to model mathematically. The kinds of problems that society expects us to solve are things like holding free and fair elections that can't be interfered with. How do you run decentralized finance? All these things are very hard to pin down mathematically, but they're real problems with real impact. And my reaction to this is I'm delighted that now we actually have applications of our previous work on distributed computing that people finally care about. But that's another rant. Okay, so what I want to talk about in this talk is I want to rethink how our notions of correctness change from the kind of naive distributed computing adversary to the modern actual adversaries. I'm going to raise more questions than answers. I'm going to propose solutions. Some of these are going to be transparently inadequate, and that's fine. My hope is to provoke thought and debate. Feel free to interrupt and protest if something I say is just absolutely too outrageous or too inadequate to the task. Now, I'm going to start out with kind of one of the oldest of correctness notions from traditional distributed computing, which are the so-called acid property. This was developed by database researchers probably back in the 80s sometime. I don't think this is an ideal formulation for the actual correctness conditions that we want, but this is widely used. You know, it's taught in textbooks and so on. So I'm going to stick with this one, despite some misgivings. And what I'm going to claim is that none of these things actually make sense in a modern sort of blockchain-like world. That the things that seem perfectly reasonable to demand of traditional distributed computing doesn't really work when we move to the blockchain world, sometimes in subtle ways. And I think this is important because you read a lot of papers that kind of assume notions of correctness that are, frankly, sometimes just unrealizable. And this results in confusion and other bad things because people haven't really thought carefully about what the systems are supposed to do. So distributed computing is full of various kinds of adversarial models. There's Byzantine, there's rational, there's all kinds of different variations, lots of parameters you can pull. Historical systems, Paxos and RAF, they assume majority doesn't crash. Most Byzantine consensus protocols assume that a supermajority, that is more than 2/3 are correct. There's refined things where you can say, well, you're either Byzantine, which means that you can be a vandal, you're rational, which means that you will cheat if it benefits you, but otherwise you'll follow the protocol, or you're altruistic, means you follow the protocol no matter what. And I don't think any of these traditional methods make sense for the kind of cross-chain deals that we're thinking of. So in this context, I want to kind of simplify things. So we have conforming parties. A conforming party follows the protocol that they're supposed to follow. I'm not going to try to attribute honesty or goodness or anything. They play by the rules. The deviating parties can do anything whatsoever. So we don't assume that deviating parties are rational. They might be acting against their own self-interest. Why is this? Well, again, this is maybe foreign government. Maybe it's a software bug. Maybe just somebody who's crazy. And they could do anything. And that's basically the model. Either you're deviating or you're conforming. We don't assume any bound on the number of conforming parties. So out of n parties, n minus 1 might be deviating. We assume there's going to be one honest party because otherwise it's not very interesting because we don't care what happens if everybody is dishonest. And why do we make that assumption? Well, the example that I give to my students, and so far none of my students have complained about this example, my students' parents have complained about this, is if you go down to the park at midnight and you decide to line up a multi-way drug deal for the people kind of hanging out in the bushes, it's probably not a good idea to assume that 51% of them are honest. And this also kind of describes the financial world. If I go around trying to do some kind of complicated bond trade, assuming that 51% of the interested parties are honest is probably also not a good idea. Okay, so first property of the acid properties is atomicity. Atomicity says that either everything happens or nothing happens. If I transfer money from one account to another, then either one gets debited and the other gets credited, or the transaction aborts and neither one happens. And this seems like a pretty appealing property, except that in the blockchain world, this is literally impossible to guarantee when all of the participants are completely autonomous. Because I can tentatively do something and then say something is fishy here and kind of roll back my part of it, but I can't force someone else to abort the transaction and roll back. So it's literally impossible to guarantee all or nothing. We need to replace it with something that makes sense in this context. So like many of these things, we'll break this up into safety and liveness properties. And I submit to you that the liveness property, the The weakest one that's of interest is you say, well, if everybody is conforming, then the deal goes through. Then everyone is better off. Safety property says if some parties deviate, the conforming parties end up no worse off. And this notion of no worse off is a little bit tricky, as you can imagine, and I'll address that later. By no worse off, well, one way to think about this is to say, well, cross-chain commerce, you can model this as a cooperative game. So here I'm going to borrow some language from game theory, nothing terribly profound. So it's a cooperative game. A protocol that everyone agrees on is a strategy for playing that game. It's a list of things you could be doing. You could be doing something else. Parties can form coalitions. You know, all those people you meet at the park might be conspiring against you, for all you know. And the result is called the payoff. So what can happen? Well, here this node represents a party in a deal. The incoming arrows are the assets that they receive as part of the deal. The outgoing assets are the assets that they give up. And one outcome, which we'll call deal, is all the incoming assets are transferred, all the outgoing assets are transferred. You know, so this is basically you commit the transaction. Another possible outcome we'll call no deal, which says none of your incoming assets show up and none of your outgoing assets go out. You end up exactly where you started. You know, this is equivalent to aborting the transaction. So these are the same as in the conventional world. But we can't rule out other kind of weirder outcomes. So we'll say you get a free ride if you receive one of these assets and you get to keep it, but you don't pay anything. You know, this might be one way that a cross-chain deal might end up. So this says you get something for nothing. Another possible outcome we'll call discount, which says you receive everything you were promised, but you end up paying less than you expected to pay. So we'll call that a discount. You know, it means that things were cheaper than you expected. And then the final one is one where you get some but not all of your incoming assets and you pay some but not all of the outgoing assets. And you know, this is basically kind of chaotic. You know, this seems like a bad thing to happen. So the actually I'm going to there was a cut and paste error and I've duplicated some of these slides, so I'm going to skip ahead. Okay. Remember, we're trying to focus in on this idea of no worse off. So how do we rank these payoffs? So I think it's safe to say the deal is better than no deal. You'd rather have the deal go through than have it completely fall apart, because otherwise, why were you doing this in the first place? Discount is better than deal because you get the same thing in both cases, but you pay less. And we assume that people would rather pay less for the same thing. Free ride is better than no deal because you get something for nothing, and getting something for nothing is better than getting nothing for nothing. You know, we're not going to try, the other rankings, you know, might be application specific. And no deal is, we're going to assume that that's universally considered better than being underwater, meaning having some chaotic outcome. There may be some situations where you might prefer the chaotic outcome, say, to not getting anything, but we're going to just assume that doesn't happen. And so I'm going to argue that each of these constitutes being no worse off, and that the chaotic outcome is worse off. So this is, you know, expressed in the cookbook game theoretic terms. What we mean when we say that the honest parties end up no worse off is that they end up in some of the one of the upstairs states and not in the downstairs state, which is a far cry from all or nothing. Okay, consistency. This is my least favorite condition because it's it's usually interpreted to say that application-specific constraints are preserved. Transferring money doesn't create or destroy money. No employee makes more than their manager, that kind of thing. That doesn't have that much direct application to the blockchain world. So I'm going to replace it with our main application-specific worry, which is why should parties conform? So we can imagine a deal where we both benefit if we cooperate, and that's good. Or I could say, here's a deal where you give me $100 and I don't do anything. And you might agree to that deal, but why would you follow that deal? So what we want to say is that conforming to the protocol, in order for any of this to make sense, should be what's called a strong Nash equilibrium. What does that mean? Well, we assume everybody starts out by playing a default strategy. And then a coalition gets together and they conspire and they decide to deviate and do something else. And in the end, we want to say, well, that won't improve its payoff. So you can't do better by defecting from the strategy. That doesn't mean people won't, because we don't assume that people are rational. Because we don't necessarily assume that our objective function is the same as their objective function. But this is kind of a, this is the application-specific condition that we care about. Let me give you an example. Here is a complicated multi-party swap, where each vertex represents a party, each edge represents an asset transfer of an asset. And the idea is that if all of these things happen, then everyone is happier than they were before. Now, under what circumstances is conforming to this a strong Nash equilibrium? Well, actually, it's a strong Nash equilibrium in this case if the directed graph is strongly connected. Strongly connected means if I start out anywhere and I follow the arrows, I can reach any point in the graph. So if it's not strongly connected, basically that means somebody's getting something for nothing. Whoever is paying that person has an incentive to not do that payment and then lie about it, and they won't be detected because the communication graph isn't strongly connected. I don't have time to do the proof, but I just want you to, the intuition here is that the reddish, pinkish part is not strongly connected. They're free riders, and Alice has an incentive not to give them any money. So if they were connected, then they could retaliate if you cut them off. So that's the next property is the one that's kind of closest to my own background, which is isolation. This is where synchronization and so on comes in. In the database distributed systems world, this is why people invented serializability, linearizability, sequential consistency. There's a whole salad of different consistency conditions used by databases, file systems, and so on. And most of these are based on the idea that a blooming, buzzing, confused concurrent execution should somehow be equivalent to a sequential execution. The nature of this equivalence varies from one condition to another. But that doesn't really make sense in the blockchain world, because if you look at these protocols, including ours, they're multi-step protocols. I'll put something in escrow, you put something in escrow. When I see you put something in escrow, I'll do something else. And so it looks like a kind of a Cold War prisoner exchange where everybody cautiously takes steps and waits for someone else to take steps. So it doesn't make sense to talk about equivalence to a serial execution, because there's a lot of interaction back and forth for security reasons. But there is something that's important, which is all of these protocols are based on some notion of escrow, meaning that if we want to transfer something, I'm going to take the asset that I'm going to give to you and I'm going to put it in a kind of a separate lockbox, usually some kind of smart contract. And then you're going to do the same, and then we'll exchange the keys that unlock these lockboxes in clever and complicated ways. So what we want to guarantee is safety property, which says that if I put something in escrow, then it can't be unlocked prematurely. Because if it could be unlocked prematurely, somebody could do kind of a smash and grab and run off with it. So we have to make sure that things are locked up for long enough until the whole deal is complete. This can be made more formal, which I'm not going to do here and now. But this is the equivalent of say, like two-phase locking, saying that you can't release locks prematurely. The liveness says that assets can't be locked up forever. Seems like kind of a silly notion at first, because this hardly happens with physical objects. But there are lots of cases in the blockchain world where somebody inadvertently locked up huge amounts of money that has become literally unrecoverable because they messed up the escrow protocol, and now the money can't be unlocked. There's all kinds of famous exploits that do this. So this leads to a kind of a related problem. So I'm going to take a very small detour here, which is a problem that we'll call lockup griefing. So we've ruled out the idea that everything is going to be locked up forever, but all of these protocols have the property that I'm going to lock up something with a long timeout, and then you're going to lock up something with a long timeout. So what happens if you take the first step, you lock up your asset for 48 hours. It's my turn to lock up my asset, and I just walk away. Now, you're going to get your money back, but 48 hours is a long time in the crypto world. Things could have gone up and down. You want to sell things and so on. So if somebody walks out of the middle of a deal, then you're kind of penalizing everyone. Now, if you explain this to people who work on Wall Street, they'll laugh at you and say, yeah, we know about this. We call them options. Because you're halfway through the deal, you have the option to either close the deal or not. And for example, we agree to do a swap. As soon as you lock up your asset, I look and see if it's gone up in value, then I'll do the deal. If it's gone down in value, then I won't do the deal. I'll walk away. But of course, you can do the same to me. As soon as I lock up my asset, you can walk away if the market is moving in the wrong way. So that means that any kind of trading becomes kind of hazardous, because everybody has an incentive under some circumstances to walk away. So what they do in the real world when this happens is that you pay what's called a premium. So if I buy an option, I say I'm going to buy, I intend to buy pork bellies next Monday, but I haven't done so. Next Monday rolls around and I say, no, thank you. Then I pay a small fee, which is what's missing from this world. So my student, Ing-J Shui, came up with this idea that we call hedged deals. This is a hedge. So the party who walks away pays a premium to the other parties. This is easy if you're doing this, say on Wall Street, but it's a little bit tricky in the blockchain world. For example, how do you identify who's guilty? You need to design the protocol in such a way that a particular smart contract can tell that it was you who walked away. If one party walks away, the other party's asset might time out first, in some protocols. So it might not be easy to tell, which one of these parties is logically at fault. There's a bootstrapping problem, because the problem of how do I pay a premium? Well, I have to put the premium in escrow. So I put my premium in escrow, you put your premium in escrow. What if you walk away after I put my premium in escrow? So it's the same problem over and over again, kind of all the way down. But the key insight is that the premium is typically a small percentage of the principal, of the amount that's being traded, and at some point you just don't care. So if I put $1 in escrow and you walk away and it's locked up for 48 hours, I don't care. If I put $1 million or 1 million Bitcoin in escrow and it's locked up for 48 hours, then I care a lot. So by kind of nesting these things, you get kind of an exponential growth in the amount of value that you're protecting. But the big issue here, what we would like ultimately, is to say that, you write your deal in a straightforward way, and we have a compiler that will go in and figure out all of the different ways it can be hedged. And we can't actually do that, but we make a little bit of a start. And this is the paper that talks about that. Okay, so I'll wrap up with the last and easiest of the properties, which is durability. So durability in traditional databases is a reflection of 20th century storage technology. So main memory evaporates when you have a crash. Disks don't evaporate. So when you come up after a crash, you've got this sort of hot mess sitting on your disk that has to be straightened out. And durability says that if I declare that a transaction is committed, that means that I know I can reconstruct it from the mess on the disk or the disks in a distributed system. What you don't want is I commit a transaction saying that, yes, your paycheck deposit cleared, now I'm going to go out and buy groceries and then have a crash and then have my paycheck not be deposited and then have my check bounced. So durability in the blockchain world has kind of a different meaning. It's often called censorship resistance. So it says that Facebook, the CIA, Elon Musk, none of these entities can prevent you from doing business. And once you record a transaction, that transaction is there permanently. The money is there. Nobody can prevent you from turning around and using it. Now, in practice, this is limited by the fact that the government can still throw you in jail for, sending money to terrorists and things like that. But that's kind of out of band for what I want to talk about here. But definitely, durability is one of the main kind of services that blockchains give you. But superficially, it looks like database durability, but in essence, it's quite different. Okay, so wrapping up, what I've tried to do here is to say that cross-chain transactions are more important than they look, because someday everything will be a cross-chain transaction, probably. And even if they're not literally blockchains, they're going to be some kind of tamper-proof repository for data that looks from the outside as if we're a blockchain, except hopefully it will be easier to use and more secure and faster, all those things. But still, the problems of trust that show up are going to be the same, no matter what the underlying technology is. We're not making any assumptions about whether this is proof of stake, proof of work, any of those kind of sectarian issues. And so what I wanted to do was start out with the sort of old school distributed computing notions of what correctness is. These atomicity, consistency, integrity, and durability, and explain why they're wrong in subtle ways, sometimes in subtle ways, sometimes in obvious ways, from the kind of post-blockchain world. And I've suggested that we replace them with some new properties, borrowing a little bit from game theory and from other areas. I'm perfectly willing to defend them. Deep in my heart, I don't think that these are the actual final answers, but I'm hoping that this will kind of raise awareness of these issues, provoke debate and controversy, and eventually will, the world will come to some kind of consensus about these things. And I really want to, again, emphasize that this is not a problem that is going to go away or even, I think, change much in its shape. That, blockchain fads come and go, companies will rise and fall, all kinds of things will happen, but people will still people who don't trust each other will want to trade. They'll want to do it electronically. And, we're going to be facing all of these same issues. Okay, so thank you, and, ask questions.
Yeah, I guess just sort of applying sort of from what you learned, I guess what we learned from the slides to the cross-chain bridges thing. So I guess just to sort of from high level, cross-chain bridges are sort of inherently risky just because of, I guess, the trust assumptions are not aligned with the previous one. I guess how do you think about cross-chain bridges riskiness from this?
So the papers that I cited conspicuously don't use cross-chain bridges. They use hash locks and alternative mechanisms. Part of it is because every day you see in the news that some cross-chain bridge has been compromised. Sometimes it's because somebody made a dumb mistake in the code. Sometimes it's a more subtle mistake. So I think the cross-chain bridges are one of these ideas that if they were to work, it would simplify the world, because you could just sort of pull in all of the assets you need, do all the trades locally, and then write them back, which is kind of a logically centralized approach. But I think, and that's what people sort of currently want to do. But I still think it's dangerous because cross-chain bridges just don't seem to work all that well. If I knew exactly why that was and how to fix it, then I wouldn't be here. I'd be running a startup company fixing it. But I'm deeply suspicious of cross-chain bridges. People have been trying to get me to change my mind, and I'm open to arguments. But there is an obstacle that needs to be overcome. I would claim that cross-chain bridges, you want them to have, kind of the same properties. All or nothing would be a really good thing to have. I'm trying to transfer my coin over here to a wrap coin over there. You want to say if something goes south, then none of my coins get transferred. You do not want, I keep the coins over here and I have the wrap coins over there, for example. I think thinking about it in the terms of that the compliant, honest parties end up no worse off is a pretty good way to organize your thoughts. Never mind whether you can always formalize that. But I will claim that this, there's two things. One is I'm attacking cross-chain bridges, perhaps unfairly, and the other is I'm insisting that these conditions actually do sort of apply to cross-chain bridges.
This adversary seems very challenging, coming from sort of distributed systems background. I want to go back to the FreeBSD double there, because it sounded like something I can sort of wrap my head around a little bit more. Instead of making our algorithms resistant to it, do you think there's any opportunity to either use legislation or other coercion or other techniques to sort of make the adversary less scary?
Well, there are a lot of protocols that rely on things like what's called staking. So I'm going to put $1 million into, which is exactly what brokers do now. You want to be a broker, you either buy insurance or you put up a bond. And so certainly that, but there is always the prospect that Vladimir Putin would love to disrupt your company. He doesn't care how much it costs. You can take the stake as long as I crash your inventory system on Black Friday, then he's happy. So you have to think through, are you willing to make these cheerful assumptions in a world that might not conform to such cheerful assumptions?
Yeah, first of all, thanks so much for giving the talk. That was really interesting. I was wondering if you could quantify a little bit more the no worse off concept. Specifically, I think it makes sense to me if you only have, like, let's say asset A, asset B, and you can say, like, as long as I have the same amount of asset A and B as I had before, you're no worse off. Does this still apply if we assign, let's say, dollar values or some other external value to asset A and asset B? Especially if the transaction or the cross-chain deal happens over like a period of time where that value fluctuates.
So you need some kind of a measure of what is better off. And so if you decide that what you care about is the dollar value, then you design your protocol so that you're not significantly worse off with the dollar value. I mean, notice here I'm also gliding over things like fees and gas costs and stuff like that. So even if the transaction aborts and you get all your stuff back, you're still a little bit worse off because you paid for gas and you wasted your time and so on. So I'm kind of neglecting that. So really what I want to say is you're not substantially or unacceptably worse off if you're honest. So you're right, there's a lot of wiggle room in that definition, but in some sense it's meant to be a little bit flexible.
Okay, so like it would still be possible to formalize the cross-chain deal given that you have some sort of external utility function provided by the circumstance.
Yeah. So you formalize in terms of your utility function, you're not worse off. Typically, gas isn't part of your utility function because we think it's too trivial to care about, which might not always be true. But so if you just change your utility function, you might want to change your algorithm because the algorithm has to be designed with the utility function in mind.
So first of all, obviously it was an amazing talk. We all enjoyed it. And I also like the fact that you were talking about like a less traditional adversary. And I was wondering whether you can like tell us a little bit more about this. I was stuck with this idea, like, are we talking just about incentives? So adversaries that might have incentives that were like we don't completely understand, or is it also a matter of they might have power that we are not aware of, or is it about like combining things that we would not?
So I'm thinking about a model where all of everybody's moves are mediated through smart contracts. So a smart contract can reject some nonsensical things. So the only thing a Byzantine player can do is something the smart contracts will allow, and that cuts down kind of the space of things that can happen by a large amount. All I can do is I can try to convince the smart contract over here the world is one way, and the smart contract over here that the world is another way. And so the fact that we don't know what their incentives are is kind of indistinguishable from saying that they could be just crazy. The question of whether they have powers that you didn't anticipate, well, that would probably break things, because you've got to kind of anticipate what the powers are, what your adversary's powers are. And you can't really design a protocol that will work against something you didn't think of.
What about combination of attacks?
Oh, so we assume here that the bad guys can form coalitions. And technically they can form coalitions and they can commit to a strategy that even if individuals suffer, the whole group might gain. So it's a pretty strong adversarial model. Basically the honest guys follow the protocol, and in the end they don't suffer in non-negligible ways. And the bad guys, we don't care if the bad guys make money, particularly if they make money from each other. So there's no notion of punishing anyone here. All we want to do is we want to say that if you want to join in, if you behave yourself, then you won't get your bank account cleaned out. And this is what is necessary to have any kind of meaningful cross-chain commerce, is to guarantee at least safety.
I had a question just when you mentioned the difficulty of cross-chain bridges. I definitely understand that there are parts of the program and they're currently being attacked a lot and the security is just more sensitive. Do you have in mind a more fundamental barrier to why maybe that will never happen or there will always be issues? Or is it more a comment about how difficult it is?
So I think it's a comment more about clearly something isn't working. Each individual case, you can explain what happened. Is there a fundamental reason this doesn't work? Well, I don't see any fundamental reason it can't be made to work. So this isn't a principled, I'm not arguing against them based on principles, I'm arguing on them based on I wouldn't trust my money to these things, which is kind of a more sincere and visceral way of addressing the question. And I would love to be convinced that you've come up with with a cross-chain bridge that is as secure as, say, hash-locked contracts, because that would make the world simpler and faster. The disadvantage of the hash-locked contracts is they have long timeouts in the worst case, et cetera, et cetera. So it's not a principled opposition. I'm just skeptical that the current state of the art really works.
I have a very open question, but I'm just a first year student. And I was wondering if there will be some opportunities in first applying the idea of blockchain to areas like distributed systems, and second, building more powerful, efficient systems to have a better support for blockchain.
So there used to be a website called "Do You Really Need a Blockchain for That?" .com, which had a flowchart saying whether you needed to have a blockchain for. There are a lot of things that people have proposed using blockchains for that probably don't really need blockchains for various reasons. understanding the distinction is kind of important, because maybe if you don't need a blockchain, maybe you need something like a blockchain. I think it's really interesting to figure out which aspects of blockchain are applicable to other areas, even if you're not going to buy the entire thing. And the subject of building distributed systems that provide better support for blockchain is what, what a lot of companies are doing. They all think they can do a better job than their competitors. And so that's also I think a really exciting, if kind of not very clearly defined area. So I think these are both kinds of good topics to pursue.
One last question, Maurice. So underlying all of this, you think there is I enjoy building infrastructure, and this talk is giving me a lot of insight or just a design directions on what infrastructure that can enable such cross-chain deals. Is the infrastructure, based on some of the conversations, it seems like you have an idea of an infrastructure already. And you alluded to hash log puzzles and perhaps generalizations. Is it already clear? In other words, is there a separate talk we can have you another time? It's already ready, or you think there's still a call to arms?
Oh, I think the current infrastructure is horrible. Sure. And nobody enjoys using today's blockchains. But it goes far beyond just having usable GUIs and error messages and things like this.
I mean infrastructure of cross-chain.
Yeah, no, I think designing blockchains to facilitate cross-chain is something that has gotten very little interest. Because each company that's building a blockchain doesn't want people to use other blockchains, so they want lock-in. So the last thing they're going to do is make it easier. And this is a mistake. But people will realize this in time. But and then when that happens, then we can all we'll all have more consulting opportunities. But
thank you so much.